for a
Oh,
while
yeah, sure, no
on YouTube. So let's just go live now. And okay, we're live on YouTube. All right, so before we start, Han, let me introduce you a little bit. So Han Zhang, or Zhang Han in Chinese, he's a assistant professor of sociology at the Hong Kong University of Science and Technology, HKUST. But before he joined USC, he was actually in the United States for quite a while, and he obtained his PhD from Princeton. And actually, he also has a computer science degree. So, combining all those expertise, he's doing a lot of really, really cool stuff. He was using text and image data, right? And like both text and image, and then combining with machine learning to study protests in China. So very cool topic and very cool method. And he also does a lot of pure methodology projects. And today's topic is just one of his methodology research. And then I will give the floor to Han.
Great, thank you so much, Yinxian. Cool. So let me say that, yeah, I'm now pretty used to the econ style where you can just stop me anytime and ask questions. So feel free to do that. Okay. So as Yinxian said, so I was working a lot with text and image data, like using machine learning, trying to dig out some useful information from like large scale text and images. So this like working paper is really kind of motivated by a lot of the exercises and lessons I learned from, just applying machine learning algorithms on text and image or perhaps other types of data. So let me motivate. So we have been seeing an increasing use of machine learning in social sciences, right? So there has been many different usages, right? So some people are saying that, some social science problems are intrinsically prediction problems, right? So we should just use machine learning to predict instead of just like writing theories about it, writing theories, right? And there's also a trend of like using machine learning for causal inference, which is perhaps one of the big topics in causal inference. And other people use like machine learning for variable selection, other different issues. So this research takes a perspective that basically some people use machine learning for measurement. So that's also a perspective promoting this new paper by Grimmer et al. So this perspective basically saying that we can generate some theoretically relevant variables from some type of big data like text, image, video, sounds, whatever, right? So that's the first step. And in the second step, we can use a machine predicted variables as either independent or dependent variables in our next step regression model. Okay, so that's the setup. And to say how popular this machine learning from measurement perspective is, I kind of searched for the published articles using this machine learning for measurement perspective in the top journals in some of the social science disciplines for the past 5 years. So I was able to find like 18 articles, so 7 in sociology, and 3 in economics, and 8 in political science. And so some of the interesting observations is like there's actually equal amount of articles that use binary predictions, and another equal amount use like continuous predictions. So all the articles that use binary predictions actually use supervised machine learning. And the continuous predictions are generated using topic modeling and dictionary method. And later I'll discuss more on this. And another interesting observation, which actually motivated a lot of the later topics today, is that I kind of found that this is actually surprising to me, because I found that most people actually use machine learning predictions as outcome variable. So this was totally unexpected to me before I did this research, but it's a useful knowledge. Okay, so let's take a real example of what this machine learning for measurement perspective is doing. So I'm taking a recent example from Francisco Cantu's like 2 years ago's APSR article. So this article asks a research question like what factors predict election fraud, which is an important question in political science. And he argues that most past research often was able to was only able to done at the micro level. So it's mirror, which election is fraud or not. So you're at the election level. And it has been very difficult to mirror like whether, there's fraud at a macro level, like whether each vote is fraudulent or not. So in order to make this, to mirror this macro level election fraud, he actually took a random sample of the image of the vote tallies in 1988 presidential election in Mexico. So this is image level, image data. So the data actually looks like this. So it's a screenshot from his paper. So as you can see from the middle of this A figure, so there are some signs that, this voter actually make some changes to the vote. Yeah. So Cantu basically hired a lot of like coders, and experts, and trying to decide which are the real, fraud, and which are just probably just miswriting or something, right? So his approach is so basically he annotated around 1,000 hand-labeled images, and roughly the same size of with vote alternations or without alternations. And he trained convolution neural networks, which is a pretty typical image classification method. And he applied the trained convolution neural network model on the rest unlabeled images, which is much larger than in size, around 52,000. So basically, this avoids the tedious task of like doing all the coding the images, right? And after he obtained all these predicted labels for whether this image has a altered vote tally or not, then he basically used this predicted vote tally alternation as as an outcome variable, and he regressed this variable on a list of independent variables. So this part is becoming like very familiar to social scientists, right? So basically have a new measure for something and then use that as a dependent variable in a regression. And the findings are like, the votes are more likely to be altered if the polling station have opposition, does not have an opposition party, or the state the states controlled by governors with grassroots experiences of managing the electoral operation. Okay, so this is a typical workflow of like using machine learning for measurement in a research article, the typical process. So here comes a problem. So basically, we all know that machine learning algorithms usually basically unavoidably have prediction errors, right? For this like specific article back into I just talked about, so his like false positive rate is around 15%, and false negative is around 9%, which is actually pretty good if you have been working with this kind of machine prediction problems. Okay, so in the presence of prediction errors, we know there have been errors, but the current practice in the social science, especially in this, the 18 articles I was able to identify, they basically treat the prediction as truth, right? So just insert them. So he got some predictions and just insert the predicted values into the next step regressions as a measure for dependent variable or independent variable. So later in this talk, I basically refer this approach as the naive regression. So just naively use predictions as the truth. So the question this talk basically will go to answer is how will the machine learning algorithm, prediction error actually impacts the coefficient estimates of the next step regression, and how are we going to crack that? Okay, so that's a big problem, and let me talk a little bit about the literature. So I was working on this for a while, and I found like it's actually the easiest solution is to just integrate the old literature on measurement error and to bring some inspirations from the measurement literature to the machine learning setting. So one of the big difference of the older like measurement, very rich but older measurement literature from the machine learning setting is that most of this measurement error literature, like all the errors in variable models, they were kind of developed with a survey or administrative data in mind, where it was very hard to quantify. You might think these people, measure some survey questions like wrong, but it will be very costly for it to redo a survey, right? So it will be very, very hard for them to verify, and quantify the scale of measurement errors in some typical like survey data. I'm not saying it's impossible, but it's not an easy problem. But in machine learning, it was actually very easy and even sort of required that everyone have to validate their machine learning predictions, right? And that automatically gives some skills of the prediction errors, which is actually one of the case to this talk. Okay, and for this specific problem, there have been several new work that explicitly addresses how the machine learning's prediction errors impacts the next step regression. So the two, I would say the two most important work will be by Hopkins and King. So they basically discuss a very simple scenario where the regression essentially has only intercept and nothing else, no regressors. And then much newer work is by Feng and Taylor. And they discuss a case where they have continuous predicted independent variables, so only independent variable. And they use instrumental variable approach. So this article didn't point out the direction of bias. So they just tell you that there's bias, but they didn't tell you which direction the bias might be. And also there's no discussions about the dependent variable case, which, as I mentioned in the very beginning, is actually the dominant approach in the applied research. Okay, so in this article, I basically shows that if you use machine predicted, especially I care about the binary variables, so that the predictions are binary. That will typically leads to attenuation biases of the slope coefficient. So there's a direction. And the intercept is also biased, but that one might be underestimated or overestimated. So there's not a clear direction. And then I propose a series of consistent estimators for how to obtain true coefficients. If you use machine predict variables in a regression, and I can demonstrate these estimators using simulations and apply the estimators to some of the published articles I collected and see if the results will be changed. And last, I'm actually developing our package, so hopefully that will help you guys to if you have ever encountered the same problem. Okay, so let me begin. So the problem of let's go into the real problem of this naive regression approach. So let's work in the simplest scenario where we have a very simple linear regression. So let's first work with this case where there's not even a control variable here. There's just a k independent variable or treatment d, or an outcome variable. So this article specifically deals with the binary predictions, so that either the y, the outcome variable, or the independent variable is predicted. And for most of our data, so this will be like in the Cantu case, that will be the majority of the data he's using. So there's no extra annotations at all. So he only have some machine predictions, right? So I call this as a primary data. Okay, so there's typically two cases, and I'm including both cases in my paper. So the first case is like your independent variable is predicted. So I use this tilde, up to the variable to denote the predictions for the observed true values. And the second case is that the dependent variable is predicted. So I just use a tilde y to denote the predictions for the unobserved true y. As a naive regression we mentioned, is just you regress correctly measured dependent variable on the predicted independent variable, or vice versa, regress a predicted dependent variable on a correctly measured independent variable. Okay, so this is set up. And so one question I actually received a lot is like, and this is my answer to that. That is like why so many people use machine learning predictions as dependent variable instead of independent variable. So my possible explanation to this is like, this is due to one of the common, perception, but maybe misconception of what this measurement error looks like. So, so in the very classical, standard regression or statistics textbook, so students were taught that if you have a mismeasured independent variable, that will lead to attenuation biases in the regression coefficient 0. So that means your regression coefficient will be biased towards 0. But if you have a mismeasured dependent variable, that will give a consistent regression estimate. Although that your standard error estimate will be a little bit larger. Yeah. So this is basically what we have been taught in the textbook. But let me remind you that this statement is true, but it's true only if you have classical measurement error. So basically, if you have binary predictions, then binary predictions always violate this classical measurement error assumption. So all this assumption is true if you have continuous variable and it holds for the classical measurement error. But if you have binary predictions, which is often the case for supervised machine learning, and that will always give you a non-classical measurement error. So that the previous statements are just not correct. To say why, so basically classical measurement error implies this formula. So your prediction error and the true value have basically uncorrelated. But if you do a little bit math, you will find that this just is not able. This is just wrong in the binary prediction case. So that means so this famous statement just does not apply here, and that is actually one of the other reasons I kind of want to do the binary prediction case first. And just to extend this idea, we can actually show that if you have a categorical variable or a bounded continuous variable, that will be like your probability, which is continuous, that is bounded between 0 and 1. And that also suffers from non-classical measurement error. So yeah, that's an extension idea. So basically, these slides tell you that if you think that you use machine predictions as outcomes, and that will give you a correct coefficient estimate, that is not true. Yeah, in the binary prediction case. So what's exactly the the bias? So before we go into that, let me just refresh your memory for some of the ways to measure machine learning predictions performance. So I think the first two, the false positive rates and false negative rates, are probably not unfamiliar to people, especially after COVID. We have been hearing that every day. Yeah, and next to the positive predicted value and the negative predicted value. So these are probably more widely used in computer science or text classification. So basically, the condition was changed. So the false positive rate and false negative rate are conditioned on the true values, and the positive predicted value (PPV) or the negative predicted values are conditioned on the predictions. So basically, for PPV, that will be if you predict something as having certain values, and what proportion of that prediction is correct. And NPV is also the reverse story. So for FPR and FNR, we certainly want it to be smaller, right? For PPV and NPV, we want it to be larger to say that the algorithm is working great. And all these four values can be calculated from each other. So yeah, they're kind of interconnected. And we need some assumptions to going on. So the first assumption is actually a very trivial one. So this assumption basically states that if you summed your false positive rate and false negative rate, and that should be smaller than 1, which is basically a trivial assumption because it's basically saying that you have to be better than random guesses. Yeah, if you have a random guess, which will yield a false positive and false negative rate both to be 0.05, and if your algorithm is a little bit better than random guess, then this assumption is automatically satisfied. And we need a second assumption. So this assumption is a little bit more tricky, and so it is called non-differential measurement error. So basically, it means that the predictions are independent of the other variables in the regression, given the true values. So this is basically the default assumption in the measurement error literature, and because that's the simplest, independence assumptions to begin with. So if we take the Cantor example, the election fraud example, so to make it into the real case. So what will be a violation of this assumption in the Cantor case? So that will be the case if, let's say another non-predicted independent variable is, whether the member of opposition party was present during the election, voting process. So if people who want to, a fraudster, he or she wanted to, have a fraud, and if he worked very hard to alter the ballot where the opposition was not present, so there's a kind of selection here. So he basically made it very hard for the classifier to detect alternation. So that'll be a sign where this independent variable is not independent from the predictions, and that will be a case where assumption will be violated. So this assumption can be verified. So you can basically perform statistical tests to say, if the prediction errors are kind of randomly distributed over some independent variables. And actually, many of the published articles did this. It's not all of them, but many people did this. Yeah. Okay, so these are the two assumptions we need. And with these two assumptions, so this is actually very old knowledge, but it gives us a very good intuition of where the bias, the direction of bias. So this is a conclusion from Jerry Hausman and his colleagues in an article like 20 years ago. So basically, the statement is that if you have a predicted dependent variable and you regress that on some independent variables using linear regression, so the linear probability model, and the regression coefficient obtained in that way will have a attenuation biases, the slope coefficient. So that is biased towards 0, because this 1 minus FNR minus 1 FPR will be a number smaller than 1. Yeah. So basically, whatever you get from a naive regression is biased towards 0. Yeah, the true effect size will be larger. To say how this 1 minus FNR minus 1 FPR, we can actually visualize it because it's actually a meaningful quantity. So for people who have done machine learning, so this like attenuation factor can actually be visualized on an ROC curve, which is a curve typically used to evaluate machine learning algorithm. So basically, a random guess is a diagonal line, and a very great algorithm looks like this. So all the way up to 1. Yeah. So basically, the vertical distance from the prediction line and the diagonal line is the attenuation bias. So basically, as the better your algorithm, the less attenuation, which kind of intuitively makes sense. Okay, so for intercept, which this is also interesting because if the dependent variable is predicted, we sometimes want estimate of correct estimate of intercept, because intercept is the average value of the outcome variable if there's no regressors, right? So still using Candace's example, if we are making predictions on vote level alternation, so one of the very basic descriptive statistics question we can ask is, what is the proportion of votes that are altered, right? So if you simply take over the predictions, sorry, let me finish. For binary variable, where the proportion of this variable is also equals to the average of that variable. So, okay, so the gist here is that if you simply take the predicted votes and takes the average or takes the proportion, and that is actually a biased estimate, because the correct estimate is actually given by this. So that means the intercept estimate from the naive regression, which is equal to you just take the average of the predicted values, is actually a biased estimate of the truth. So the formula is given by this. So this time it's no longer always attenuated. It can be over or underestimated. So this finding is actually basically equivalent to Hopkins and King's article, though they motivate in a slightly different way. Yeah. Okay, so now let's talk a little bit the more complex case. So in the previous slides, I was talking about the predicted outcome variable in a linear regression. So I think in sociology, people usually use logistic regression to model the binary dependent variable, right? So if we make it a little bit more complex for logistic regressions, then all the closed form and analytical formula does not exist. So there's not an easy way to translate to have a formula for the exact size of attenuation for the regression coefficient. But still, we could have the marginal effects formula. So that means the marginal effect is still attenuated if you were to run a naive logistic regression. And this formula also holds if you use other generalized linear models like probability or something else. Okay, so the last message is for the predict independent variable case, which was, the conclusion was first identified by Dennis Agner, even like this is already 50 years ago, right? So basically the story is like, if you run a naive regression on a mismeasured variable, that still leads to attenuation biases in the slope coefficient. And in this time, the correction term, so basically attenuation factor changes a little bit, yeah. The format is similar, but it changes to the PPV plus NPV minus 1. Okay, so basically a quick summary here is like, if you have a naive regression, just regress, put your predicted values into a regression. And that would typically lead to attenuation biases in the slope coefficients or the marginal effect. And this conclusion actually did not include control variables. So if you have control variables, it was also pretty hard to have a closed form formula to write down the exact attenuation factors. But typically in simulations, this is both the previous research, but also my own simulations. So the attenuation tendency is basically approximately correct, unless you have like really crazy correlations, basically like over 0.9 correlations between some of your variables. Yeah. So that's only would occur in some of the very special cases. Okay, so this section basically tells you that in general, there's a tendency that, if you use naive regression and you will obtain attenuated slope coefficient. So how can we recover the true coefficient? So that's the topic for the next. So basically the intuition is very simple. So like as we previously already seen, if you already know the FNR and FPR, so because we can have a closed form formula, right? So or we kind of already know how to estimate that. If you are able to calculate these error rates, and it's basically done. But the problem is that by definition, the FNR, FPR, or the PPV and NPV, they cannot be calculated on the primary data, which is much larger data that you want to analyze. Or otherwise, if you don't think this is the case, otherwise, you can just use the true labels from the primary data as variables, right? So you don't even need to use predictions. So basically the solution is very simple, and this is actually unique to machine learning setting. I don't think this applies for survey data because it will be very hard to require survey researchers to have validated data. But if you are ever doing machine learning, this is basically even required to have some sort of validation data, which you have both true labels and their predictions, and from which you can calculate the error rates. So that's turn to next. So first, we have a very simple and perhaps the most popular scenario. So that will be the case you actually train your own model, right? Like the Cantu example. So basically what you're doing is like you have a very large scale like text or image data, and you randomly sample some data and then annotate them to create training data, and then hold out some proportion of the training data as the validation data, right? So you have a very nice split of like primary data, which is a much larger data set you want to run regression on, and the training data to train your algorithm, and the validation data that we also have the predicted and true labels. And in this case, validation data actually automatically exists. So yeah, nothing surprise here. And I think it's worth discussing slightly more complex cases. That is, there's actually no training data. So that could occur in cases if you're applying some supervised like machine learning model trained by other people, which has actually become more and more popular, especially in the deep learning age. People are just take whatever pre-trained models from other people and then apply that to your own algorithms. Or you're using dictionary method for text, where you're just applying some dictionary and calculate the word count, and there's actually no training at all. Or unsupervised method like topic modeling or something else. And you can still have a set of validation data, but you need a little bit effort. So this is basically you need to random sample a small subset of your primary data and annotate them and to create the ground truth labels. And in that, you can actually still evaluate the performance of your algorithm. And regardless of which case, whether you're training your model or the other cases on this slide, and we all got the validation data, and that allows us to actually estimate the error rates. So this is basically like the computer, the theory part. This is the statement is like if you have a validation data that are actually never touched or never seen by the training algorithm, and the FNR and FPR calculated on this kind of validation data set will be a good approximation of the FNR and FPR on the primary data. Yeah. So this basically tells us a way to calculate the FNR or estimate FNR and FPR using a smaller validation data set, and use that estimated values to apply to the primary data which you're going to run regression on. And yeah, this is basically a more formal statement of what I just said. So we need to have a true validation split, and the validation data should never be seen by the algorithm, or otherwise the FNR and FPR estimates are biased. Okay, after these assumptions, and then we can very easily estimate FNR, FPR, or PPV and MPV by just creating what machine learning people call confusion matrix, by basically tabulating the four cells and use a number of like true positives, true negatives, false positives, and false negatives in the validation data to estimate FNR, FPR, PPV, or MPV. Yeah. Okay, so from now on, we have obtained the estimates for these four error metrics, and then next step is to use them to obtain corrected regression coefficient estimate. So first, like if we have no additional control variable, which is the easiest case, and we already derived the formula like in several previous slides. So it was just flipping the left-hand side and right-hand side of the equations, and we can obtain some easy calculation to obtain a corrected regression coefficient. So this is basically, the first step, you run regression using the predicted values, predicted dependent variables, and then you calculate FNR and FPR, and then you divide your regression coefficient by 1 minus FNR minus 1 FPR, and you get a coefficient that is larger in size. Yeah. And also for variance, that's not hard. For this very simple case, we can just analytically derive the formula. And in the variance case, you can say that now the factor is on the denominator, and the standard errors also get larger. So that means, after you do the statistical correction, basically your coefficients, the absolute value of your coefficient will become larger. That means, your effect size is larger. But the standard errors will also be larger. So you basically get a larger coefficient, but also a larger standard error. So you don't know whether your effect will still be statistically significant, which kind of makes sense. So basically what we're doing here is like we're taking into consideration of the machine's prediction errors, right? So once we take into this additional errors in estimating regressions, then we ought to have a more uncertainty, right? So it's very natural that the standard errors are increased. Okay, so this is a simple case, and the next several slides are like more mathematical details, but I will try to convey the intuitions. So intuitions are pretty straightforward. So if we have additional control variables, like we don't think we can't derive the closed form formula, so we just do the maximum likelihood estimation, the standard way to estimate this kind of problems. So the K of MLE approach is actually to express the observed data probability as a function of true data probability, which kind of links to the true regression coefficient. So this is a likelihood function, which is a product of the observed data probability. And if you play with some of the Bayes rules, and you can find that this observed data probability is a function of the true data probability. Like I don't have prediction here, so and which links to the true regression coefficient. Yeah. So basically, the math is not super hard, but I think the intuition is also straightforward. And so this looks like a pretty complex, but yeah, I think basically you need to do some math and express all the observed data probability into a format of the true data probability and just write down the detailed likelihood function and solve this, and you can get a good regression coefficient estimate. Okay, so this is an MLE case. And I also worked for two other more complex cases. So the reason is that, so typically we have like pretty small validation data set. Like they're typically ranging from like 100 to around 1,000. Like in Cantu's case, I think his data set is only around, his validation data set has a size around 150. So essentially you're calculating, the four FNR, FPR numbers from like 150 observations, which can have some estimation uncertainties. So both the ML analytical and MLE estimators basically, treat the FNR and FPR estimates as fixed. These are just fixed numbers from your validation data. So in order to take into consideration of this estimation uncertainty of the FNR and FPR, so I designed two other estimators. One relies on Bayesian approach, and the other relies on Bootstrap approach. So basically, the idea was to express, especially for Bayesian, the idea is to treat the error rates not as fixed quantities, but as random variables, and to allow it to vary according to, like specifically here, I'm basically letting it to vary by a beta prior. So that's basically a conjugate prior. And all the other part of the regression kind of follows a very standard Bayesian logistic regression setup. So this is kind of a mix between the standard Bayesian stuff with a little bit different. That is, we kind of integrate the FNR and FPR part into the sampling of the data. Yeah, I think I'm kind of skipping this pretty quick. So if you have questions, we can, always chat in the end. And the Bootstrap also, it's not hard. So Bootstrap idea is basically to resample the validation data. Yeah, that's okay. So we have like observed validation data, and with that you can calculate FNR, FPR, which is a fixed value. But if you draw resamples from validation data set, like with equal size, then you can calculate many FNR and FPRs, and you basically have a distribution of your error rates. And for each resample data set, you can calculate, one set of regression coefficients. And finally, you just, take the whatever mean standard deviation or quantile functions to apply the, the estimates, understand errors, and confidence intervals. Yeah. Okay, so that's the two additional estimators, Bayesian and Bootstrap, which can take into consideration of the estimation uncertainties of the error rates. So far, what I have been talking about is like the case if we're using machine predictions as dependent variables. So equivalently, I also derived everything for the linear regression case. That is using predictions as independent variables. But the intuitions are pretty similar. So yeah, I'm just going to skip the details. Okay, so here comes some simulations. So this part basically shows that the estimators works in an ideal scenario. So works in a way that we expect them to do. So I basically simulate some fake data, and the true regression coefficient for D is 1, and FNR and FPR I kind of set it to be both 0.1, which suggests a pretty good machine learning algorithm to be pretty good. And I set the validation data sets to be 100, and primary data is 9,000. And to draw the data following this procedure, and to see how the naive regression coefficient estimates differs from the estimates using the estimators I just talked about. Okay, so here's a result, and so this naive estimate clearly deviates from the true values, which are the the dotted lines in each of the plot. And all the like MLE and Bayesian and Bootstrap estimators kind of recovers the true coefficient. And very naturally, like Bayesian actually has larger confidence intervals than the MLE, and Bootstrap have even larger confidence intervals. And which is also the case for other cases. And this validation this is, sorry, I don't think I mentioned this. So this is basically a very simple approach. Like you have a validation data set of say a size 100, and you just run a regression on this very small data set, which is theoretically guaranteed to be okay. But certainly due to a small sample size, it's have a very large confidence intervals. Okay, so this is the predicted dependent variable case, and we can also, with the Bayesian and Bootstrap, we can have a confidence interval for the FNR and FPR too. So that's one of the advantages here. Yeah, so as we expected from the previous result, we can say that the Bayesian here actually have a smaller standard errors of the FNR and FPR estimates compared with the Bootstrap method. So this is like specific to the Bayesian Bootstrap. Like if you use MLE, this does not exist because basically as the MLE treat the FNR and FPR as fixed quantities. Okay, the simulation tool are basically very similar, but flips the equation by using predict independent variable case. And also the plot looks more or less the same. The naive regression kind of, in this case, actually overestimates the intercept and underestimates the regression coefficient for the predicted independent variable. And for the third variable, so this one is not predicted and it's uncorrelated with the predicted independent variable. So that one actually, the regression still gives a good coefficient estimate. And in this case, the Bayesian actually have a larger confidence interval than the Bootstrap method. And of course, both are all having larger confidence intervals, wider confidence interval than the MLE approach. Okay, I did many other simulations. One simulation that might be useful for applied researchers is that I basically use a sim setup that varies the size of validation data, and to say, what is a good choice of the validation data set. And so this is a predicted dependent variable case, which sort of suggests that if your validation data kind of reaches around like 500 observations, then the reducing MSE kind of is no longer that salient. And also for the predict independent variable case, that's the same story. And there's many other simulations I did in the working paper. So vary the size of error rates and try various model misspecification cases. And it seems like all the proposed estimators in this article actually, they basically consistently give smaller MSE than the naive estimates, which is, you just take prediction as they choose. Okay, great. So finally, we have some applications. I basically, took some examples from the published articles I identified, and to rerun the model using the naive estimate, which is basically what they offered in the paper, in the original published article, and also apply that with my own method. So this is a Cantor example we have been seeing several times. And his prediction, as I said, is pretty good. And I would say, pretty good. If I were to do a study and I found FPR and FPR to be this high, then I'm thrilled. Okay, so the left column is basically, if you read his original article, this is what he presented in the published version. And this is after the MLE correction. And as you can see, the coefficient, so effect size basically gets larger, which is actually good. But also, all the things are, if we care about p-value, all the things still stays as statistically significant. So that's great. And here's a plot for more regression coefficient. So the red one are his original, estimates by just trading the predictions as they choose. And the others, like the non-red ones, are the other estimates from my estimators. So we can say that all of them increase this confidence widen the confidence interval, which makes sense. But all of them also makes the effect size larger. So this is actually a good example, I think, because the results are pretty robust, right? And not only that, but also we basically found everything, every important factors to originally identified were also, still stayed as statistically significant. So that's actually a good story where, you had a larger effect size. We have a larger effect size now, and also everything stays significant. Okay, so here's a not that fortunate example where I kind of found the result or the conclusions might change if we revisit this study using my proposed estimator. So this is an article by Category and Min and published like in 2019 in APSR. So basically, this is an article. The research question is about whether White Houses are willingness to use forces during the Berlin crisis will be changed by like private statements, public statements, and articles from New York Times in the same time around that event. So this is a case where the author actually used both machine learning algorithms to predict both the dependent variables and the independent variables. And this is actually, I think, maybe one of the two only articles I can find, because typically people only use, predict one side of the equation. And this is the article I found, like he actually predicts both sides. So the dependent variable is predicted, and that is, the archive data from White House's, released archives, and that quantifies whether, these documents describe, the White House is willing to use force or not. So it's a binary prediction. And the two independent variables are, private statement, and also from declassified telegrams from the US Department of Defense. And another predicted independent variable is the public statement during the Berlin crisis from the Foreign Broadcast Information Services data. And the third independent variable comes from New York Times articles. And this is non-predicted, so it's coded by expert. And we know expert can make errors, but let's not assume that everything said by the experts are definitely correct. Okay, so his procedure is also is a very standard supervised machine learning. So, create some training data as a random sample of this White House documents, the telegrams, and the Foreign Broadcast Information Services release documents, and to train an algorithm to classify them as, whether they expressed support to use force as a Berlin crisis or not, right? So it's a binary prediction. And one thing that makes this a little bit tricky is that, so the authors actually, they originally have a document level binary prediction, right? So whether, the document expressed support use force or not. But after they got this document level predictions, they then aggregate the documents into weekly level counts. So that's from a binary to a weekly level counts of the documents that express corresponding categories. So as we said, so this is a time when we should use the intercept correction formula to obtain the corrected mean of the predictions, because if you simply sum them over, it's not correct. And of course, this operation actually relies on assumption that the machine algorithm's classification rates, error rates, does not vary by time, which which is a strong assumption, but I can't verify that, and because the author does not give a more detailed breakdown of whether their algorithm is more correct in certain times than others, which is also a hard problem because they only had around 150. I think from one outcome they only have 150 documents. So yeah, if you split them into weekly levels, then only dozens left. Okay, so after this, and I basically rerun my model and compare this with their original estimates. And in this case, because as you can see, their original estimates are already pretty close to zero. So this will be a marginally, if you force them to use p smaller than 0.001, then probably they will already no longer be statistically significant. Okay, so after applying my estimator, and because the estimator will increase the effect size, but also increase standard errors. And this is a case where some of the effects the original article thought are important actually becomes not statistically significant. And I know, like, being this p-value calculation, like being statistically significant doesn't mean that being statistically insignificant does not mean you have a unimportant conclusion. But what I want to say is, like, this will be a case where you probably should be more careful about what you're doing, especially you kind of wrongly just use machine predictions as variables. And if you don't take consideration to the prediction errors, and that might, at least lead researchers to rethink their conclusions. Okay, so these are the replications of the two articles I found, and I've done some other replications in my working paper. So these are some observations I found after I did this calculation. So it's actually not uncommon that researchers first generate some binary predictions as a document level, like tweets or articles or whatever, and then aggregate them into like week or year or geographical regions into some groups. And this is a naive approach, again, that will give you biased estimates of regression coefficient, because simply summing or averaging over machine predictions will give you a biased estimate of the true counts or proportions. And this is sort of beyond the scope of these articles. This article is already too much. And in the previous replication, I basically assumed that the error rates are constant across group. At that time, the group is time. And this assumption is certainly likely to be violated. And so that's basically a future direction I kind of wanted to work on a little bit more. Okay, and another observation is like, so all the examples I talked here so far actually use supervised machine learning, right? So what about, all the other cases, if people use dictionary method and unsupervised method, especially like topic modeling? I think for dictionary method, that is easier. And because we have a very clear defined dependent variable, just no training data. And so it's a good practice that actually the article I found, I don't think the authors actually validates their dictionary method predictions, which I hope they did. But at least in theory, that is easier and could be done. And for topic modeling, I think that's a little bit different realm because I don't know how many people know this, but the structured topic model, which is a pretty popular method, it kind of basically shares the same spirit of this article. So the question the structured topic models wants to address is like, sometimes we just like do a topic model and trying to depict the topic proportions by time or by region or whatever, and just use them as regressions. And we know this topic proportion can still have estimation uncertainties. So the what STM is doing essentially is to take into consideration of the estimation uncertainty of the topic proportions in a regression analysis. Okay, so in a spirit, I think the STM is similar to this article. So the difference is like STM is kind of specifically designed for extending basic topic modeling, that is LDA. And this article is more like a model agnostic approach. So I really don't care about what specific machine learning model you're using, as long as you can calculate FNR, FPR, that sort of error rates, then it's fine. Okay, so let me finish. I think time is also pretty apt. So the conclusion is like if you use binary machine learning predictions directly in a next step regression, then typically the danger is that the slope coefficient will be attenuated towards 0. And this is true regardless of whether you're using your predictions as independent or dependent variable. And the intercept can be under or overestimated, so depending on specific values of your FNR, FPR. And in the paper, I kind of propose a series of estimators to obtain the consistent estimates. And so take-away message is like, if you apply these estimators, then typically the effect size will be larger, but the standard error will also be larger. So that's kind of a trade-off. Yeah, so the contributions. Basically, this article kind of actually bridges a very rich measurement error literature to the more applied machine learning setting when people are just using big data to do whatever measurement. And I implement and propose a series of estimators to consistent estimate regression coefficients. Okay, so this is the final slide, and I have a working paper online, which is kind of a version several months ago, and I think I will make some revisions after this talk, and also develop a package. Yeah, and so yeah, let me stop here, and thank you all for your time, and yeah, I look forward for your questions.
Thank you so much, Han, for this fascinating project. There are a lot of technical details. We probably need to go deep into your working paper and like just go through it. But let's open the floor to the audience first. I see we have quite a few methodology experts here. Do you guys have any questions for Han? Yeah, Hongwei, go ahead.
Oh, thank you. Well, first of all, I apologize for being late. I was anyway. I think I met Professor Zhang at Princeton. We passed in the hallway, I think, and Yuxie introduced us.
Oh, yeah.
I remember there was a computer science PhD student there, and I think I also attended your talk last year. You gave a talk about I think an image as data or text as data.
Yeah, that's another direction I've been working.
Yeah. So I'm fascinated by your work. I do not do machine learning or big data myself, so I'm just a casual audience and just keep a methodological interest. So I didn't quite catch the first replication study you mentioned at the beginning. I kind of gathered the second. Sorry, I'm at home. My neighbor is talking. I think I have a better idea about what the second study is. But I guess my major question is I miss the motivation for using predicted dependent variable or independent variable for the next step, kind of like a analysis. Maybe that's very common in big data analysis. So could you maybe elaborate on the?
Sure, of course.
Yeah. Thank you.
I think basically this comes from like if you have like very large data set, like millions of documents, then you don't want to read them one by one, because that would take forever. So instead, what people usually do is like they randomly sample some part of their data, and they use this data and annotate them and tell these are the true like images, like whether the vote is altered or not, or like in documents whether the documents positive or negative, whatever, and use that part to train the machine, basically to teach machine, and then finally apply like the machine algorithm on the much larger data set. So this is basically a way to help people to quickly code a lot of data. Like in this example, like I think what he did is like he got around 53,000 images, but maybe perhaps he found it's like it's too time consuming to hire people to code every of the images. So instead, what he did is just, carefully hand coded around 1,000 images, and then teach machine. Okay, these are the examples of, those are altered and those are not, and then apply the model on the rest on label data. So that kind of greatly saves the time and energy. Yeah.
I
So
see.
this is
So
a really common approach in, I would say, applied machine learning.
yeah, I see. So this is more like using machine learning to process a large volume of data.
Exactly.
And because you kind of, in many applications, you have to categorize like one observation as being a binary outcome, right? So that's kind of a typical application. Okay. Yeah, I was thinking about the second example where you categorize, well, no, I mean the original authors categorize those documents into like a yes and no, and I was just thinking, if I were to do it, I will probably not dichotomize the labels of each document, right? So maybe there's like a predicted continuous scale, like this document signals 70% willingness to take some action. I was just talking with my friends about the current situation in Ukraine, and I was listening to the president's address to Congress, and I was thinking, wow, all the congressmen and women may have a different percentage point of willingness to go into war, right? At this moment. So I would not I would not do like a dichotomized labels.
I totally agree with it. So there's not an intrinsic principle that you should code your documents or images into binary or continuous values. And it's just like from the reading the literature, I kind of surprisingly find that if nearly every paper that is using supervised machine learning is creating this dichotomized coding. So my possible so first I don't know why they did that. My hypothesis is that probably it might be easier for maybe you're giving the coding to undergrad students or some Amazon Turkers, and probably it will be easier for them to just make a yes/no decision instead of letting them to give a score like from 0 to 100. Yeah, but I agree with you. I don't think there's you should intrinsic, you should prefer binary or continuous. I think it's kind of depending on the difficulty of task.
Thanks so much. Thanks so much.
Oh yeah, thanks a lot. Yeah.
So Han, are you saying that, so on your last slides, are you saying that when we talk about topic modeling, because I myself use topic models, are you saying that if we use STM, I don't need to worry about this bias? Like STM take care of the bias already? Is that what you're saying?
I think in spirit, yes. So what STM is doing is that if you use topic proportions and you take that out and you insert that into some regressions, and in that approach, you are essentially discarding all the estimation uncertainties of the topic proportions. Yeah. So in that way, if you let me say it in this way, if you trust topic models produced topic proportions as a measure of something, then I think I agree with you. That's the way to go. And an alternative approach, which is actually suggested by many people, but I don't see it's very often used in applied research, is that they basically call this as external validation or something like that. Okay, so what they're saying is like, okay, if you run topic modeling and you have some topics like politics, economy, whatever, culture, and you have some topic proportions, like a document is some proportion economy and some proportion politics. And what they're saying is that you probably should do external validation by hiring another set of people and let them to rate the documents and give maybe a binary, but also continuous evaluation of do they agree with topic modeling's prediction or categorization that this document is 50% politics and 50% economics. Yeah. So if you're taking that external data, then that actually falls into what I'm talking about here. Is because you have some external data to validate whether the topic proportions are correct or not. Yeah. But let me, as I said, you are just willing to assume that topic modeling's internal results, what topic modeling, the estimation of topic proportion gives is a correct one. Then I think STM is at least that's what I can think of to nicely incorporate the estimation problems into the regression coefficients.
I see, gotcha. So, but then in that sense, STM is definitely more reliable than LDA, right? Because
yeah, I would say for social science, yes, yeah, for social science purposes, especially if you want to integrate some topic, document level, whatever variables that are from topic modeling to the some non-text based variables.
Gotcha. Thank you. That's awesome. Okay, I also saw Yo Wu. She's asking a question in the chat. She said, "How strongly do you think the attenuation effect affects findings in so many papers that use this approach? Does it invalidate all the findings?"
I don't think it invalidates all the findings. Like actually in this Cantu example, as you can see, that actually makes the effects stronger. I mean, of course, it widens the confidence intervals, but because the original effect size is so, statistically significant, like here, like at the 0.001 level. So even if you increase the confidence interval a little bit, and the result still stays statistically significant. And to make it even better, the effect size is larger, right? So there's even more, the effect size is even larger. And this will be an example where, the result is slightly different. And I think the part of the reason, as you can see, the original estimates are already, I shouldn't say shaky, but at least not as statistically significant compared to the previous example, right? And also, I don't think I give the exact FNR and FPR number here, but their error rates are larger than the previous study. So in the presence of these two, effect, like their effect is not that statistically significant, and their machine prediction errors are also larger, such that we observe basically changing from slightly statistically significant to not statistically significant. Yeah, and I think basically this is case by case. I don't know in which exact case, whether the prediction will be invalidated. I can just say like if the machine's prediction errors are very large, then or your original estimates are just barely statistically significant, then you probably have to be cautious.
Thank you.
Which is kind of intuitive, makes sense, right? If you have like 30 or 40% of your machine predictions are wrong, then you probably should not even use that. Because I don't know how you trust an algorithm whose prediction like 40% wrong, right?
True. All right. Do we have more questions? You can raise your hand or just type in the chat if you don't want to speak up, or if you're on YouTube, we have a few people watching this talk on YouTube. You can just put your question in the chat and I will read it to our speaker. And I think Yo-Yo has a follow-up question. She asks, does the correction for attenuation run into the risk of p-hacking in the sense that it can boost the findings?
That's an interesting question. I don't think it's a p-hack. I think it's the effect size. And I shouldn't call it hacking because I believe like this is true. Or at least if you truly believe your machine predictions contains errors, then you should correct that errors, which is brought into the regression coefficient, right? I think if you are to talk about p-hacking, then that method should reduce the p-value. Right? Like this correction here actually increases the p-value. So I don't think that falls into the p-hacking scenario.
I think what she meant is because we will constantly get a larger effect size. right? For the coefficient, it's always larger. The intercept might be larger or smaller, but the coefficient estimate will always get larger after the correction.
Yeah, I get that.
So it's like metaphor of p-hacking, but not about p-values.
Yeah, that's a good point. And I still don't think it's p-hacking because I sincerely don't think the estimated, the regression coefficient, if you were just to treat the predictions as truth, is correct. Yeah. And especially in very simple scenarios, we can actually exactly calculate what are the biases, right? So, and even for the more complex cases, we can't exactly calculate what are the bias. We still, we still kind of like, I think the spirit is similar. So because we know that you're including a variable that is wrongly, that have prediction or measurement errors in regression, that shouldn't be that correct. Yeah, I think if you are really worried about this, then probably you should actually use the Bayesian or Bootstrap method, because that will also take into consideration the estimation uncertainty of the error rates itself. So that should give you a safer or more conservative estimates.
Your R package will provide all those different approach, right? You can choose.
Yeah.
I imagine you can choose whichever approach you would like to use to estimate.
I'm trying to find a time to revise it. Yeah, and just getting a little bit to write codes, but hopefully I can have better documentations and examples. Yeah.
Awesome. Any more questions from our audience? So it seems that we're good here, and we're all really impressed by your work. I can see this is already a pretty mature research paper, and more importantly, you're even writing this R package, which will benefit a lot of us, I believe. So thank you very much, Han. And I also want to thank all the audience that make it here today, even though we changed the time. And actually, it's already past midnight in Hong Kong. So thank you so much for coming by and staying with us, Han.
Thank you so much for coming.
Yeah, thank you all so much.
Great, and feel free to send me any questions.
Yeah, so this is Han's contact info, and this is also you can also see his working paper here, and our package is under